Hi, welcome to The Art of Code. My name is Martijn, and a while ago I was asked by patrons to make a video on how to make cool looking reflections, and I played around with a bunch of different concepts, and in the end I ended up with this little Newton's cradle that you see behind me. Over the next few videos I will go through how to model this thing, how to animate it, how to add materials, and last but not least how to add reflections. I got a fresh mug of tea, so if it interests you to learn about this, then let's get started. Alright, so this is where we are starting. We're starting with the ray marching starting point. The link is in the description below. If you want to know how to write a ray marcher yourself, I made a video specifically about that where everything is from scratch. And if you follow that, you should be able to write one yourself. But for now, I'm just going to start here. Otherwise, this video is going to get too long. So we have this scene here with just a cube that I can spin around. And the first thing I'm going to do is I'm going to turn this cube into the base of the Newton's cradle. And for that, I'm going to go to the getDist function over here. And here I'm getting the distance to a box. The dimensions of the box are 1, 1, 1 in this case. I'm going to make the base a lot thinner, let's say 0.1, and then I'm going to make it half as wide as it is long. So I'm going to do 0.5. And now let me also zoom in a little bit. So over here where I get the ray direction, that last point there is the zoom factor, so I can just zoom in like that. And this is the look at point, which right now it's at the origin, but I'm going to look slightly higher so that we can see better what we're going to build. All right, so let me go back here. All right, so I want this base to be rounded, so I don't want it to be sharp like this. So for that, I could just subtract some value from this to make a rounded box. And now, obviously, I want the roundedness on the top and not on the bottom. And also I want this to be thinner, so I'm just going to slice it through the middle here. And to do that, I'm going to use a Boolean. And for that, I can use this. I can say the maximum of d and p dot y, which is the height of my ray marching position, which is basically just a plane. So right now it's going to cut off the top, but we want it to cut off the bottom. So basically, like if you want to know what it's cutting, I could just do a union instead of a subtraction, and then you could see what that is, because it's actually just a plane. It's an infinite plane. P dot y is just a plane that is at 0. And in order to subtract that, you have to make it negative and take the maximum of the two. And then it subtracts that plane. And it gives you that. So that is good enough for the base. So now let's do the bars, so the little bars that the balls hang off of. And for that I'm going to use a 2D box distance. So this is the distance to a 3D box. Well, we can do a similar thing with a 2D box. So let me copy this here, so this is the function that gives you the distance to a 3D box. I could just change it a tiny little bit to make it the distance to a 2D box. So instead of a 3D position, I'm going to throw in a 2D position. Instead of a 3D size, I'm going to throw in a 2D size. And then over here, where I get the maximum between p dot x, p dot y, and p dot z, I'm just going to get the maximum between p dot x and p dot y. Okay, so that should give me the 2D distance. And so now let's get bars equals SD box. And so it's named the same, but we're going to, instead of a 3D position, we're going to throw a 2D position into it. And then the compiler will know that it should take this function instead of that function. And so I want that box to be standing upright, so up and down is y and left and right is x, so in the xy plane. And so I'm going to go over here, I'm going to say p dot xy, and then for the size I'm going to let's just start with 1, 1, see what that does. And so this is a 2D distance, but I'm still marching in 3 dimensions, right? So so what I'm going to do here is I'm going to, so this is the 2D distance if you were inside of the plane that the 2D shape is in, but we're not inside of the plane, we're like either above or below the plane. And so what I can do for that to get a 3D distance, I can make this into a vector 2 that has the square in the xy plane, and then I'm going to throw the z into it as the second component of that vector. If you want to know how this works, check out my video on how to do the distance to a torus, and it should become a lot clearer, because I have to kind of go through this a bit faster. So now I have this vector. Now I can get the length of that vector, and that would give me the distance to that box. So let's see what that looks like. So I do d equals the union of d and the bar. Okay, that gives me an infinitely thin box over there, or an infinitely thin bar. And so now I can just subtract from that something, and there is our shape. Okay, and similar to how I rounded this box over here, I can also round this shape, because I can just go over here at the end of this box, and I can just subtract something from it. So I can subtract 0.1 from it, or maybe 0.15, something like that. And then obviously I'm going to have to make it smaller to make it fit properly. So I'm going to go, let's say 0.8. Okay, so that seems to work. And then also we're going to have to cut the bottom off of this thing. So I'm just going to, where I'm cutting it here, right? So this is cut off the bottom. I'm going to, let's just cut that out and put that all the way at the end so that it automatically also cuts off the bar. Okay, now I'm going to make the bar a little bit higher. So let's say 1.4. I think that is good. Let me move the camera up a little bit more, or the look at position. So here I'm looking at the position that's 0.5 off the ground. Let's make it 0.75 so we can see this thing. All right, so now let's go back here. And now obviously I want a bar not in the middle, but on the side. So for that, so this thing just, well, this entire thing just gives you the distance to a bar that is at the origin, right? It's at the origin for x and y as well, but also for z, right? And the origin for z is just right in the middle of the cradle. So if we want that to appear somewhere else, we're going to have to remap the origin so that it is somewhere else. And so in order to remap that, I could just, if I subtract from there, you can see that it moves over. And the reason why is because let's say over here p dot z is 0.2, is 0.2, right? Well, then you get 0.2 minus 0.2. So it remaps that. It remaps the position where you want it to the origin, and that's kind of how that works. So let's say at 0.4, and now we want 1 on the other side as well. And now I could copy this entire thing, and I could do the union of the left bar and the right bar. But in this case, because it's a simple symmetry, we can just make it that instead of using the z value here, the normal z value, which is positive on this side, and as you get closer to the center, it goes all the way to 0, and it's like 0 in the middle, and it goes negative over here. Well, if we just take the absolute value, then it would go from positive down to 0, and then from 0 back positive again. And that will make it that the other side you get for free, pretty much. Pretty cool. All right, so that is that. Now let's put in some balls. So I'm going to go, and also let me just call this base. Okay, so I'm going to say over here, base, float d equals base and bar. Okay, so that should be, that's the same. So let's put in some balls. So I'm going to do float balls equals, and we can start with one ball, which is just a sphere, right? The distance to a sphere you get by just getting the length of the ray marching position, if you want the sphere at the origin anyways, minus the radius of the sphere, which let's make it that. So let's see, that will probably put my ball right in the middle of my base, but let's have a look. So let's union that into our final distance value. So d and balls. Okay, so we can't see it because it's actually inside the base. So we're gonna have to move it up a little bit. So again, the way to so this is the distance function for a sphere at the origin. If we want that sphere to appear anywhere else, we have to remap the origin. And to remap the origin, we can just subtract from here. And so from left to right, we will still want it in the middle. From top to bottom, we want it higher. And then from side to side, we also want it still in the middle. So that should be good. So there is our ball. Perfect. All right, now I want to add like a little ring to this ball at the top, and I want to add like some filament that goes from here to here, and then afterwards I'm going to have to make 4 other balls. So it's cleaner if I put that in its own function, so I don't have a whole bunch of repeated code, which is never good. So let's do that. So let's just cut this out here, and let's go over here. And let's say float SD ball, assign distance to a ball, and that's going to take as an input a position P, and then let's make this. Okay, then we can just return that value D, so that shouldn't change anything. Let's check SD ball, and I'm going to throw my P into it. And it didn't change anything. Actually, I do want to change something. I want to take this out here and put it over here. So that this is already centered on the ball. We don't have to do anything. So that didn't change anything either. All right, so that's the ball itself. Now let's add the ring at the top. So float ring, and that's just the distance to a torus. And I mentioned it before. Check out the video in the description below if you want to know exactly how I derive this. I'm just going to do it quickly. So first I'm going to get the distance to a circle, and so the circle, like the way the ring is oriented like this, right? So it's going to go, is it like this? Yes. So there's a little ring over here like this that is embedded in the XY plane, right? So X is like this and Y is like that. And so I'm going to get the distance to XY, and then that ring has a certain radius, so let's say 0.05, and then I'm going to make a vector out of this, vector 2, that has this in the X component, and in the Y component that has where we are from side to side, which is the Z component. Actually, let me just get rid of this here, and I'm going to get the length of that minus the small radius of the torus, which is 0.01, let's say. And again, I realize this is very fast. If you've never seen this before, you will not understand, but go check out the video in the description, and you shall be enlightened. Okay. Okay, so here we do D equals D comma ring, and that ring is going to be right at the origin, and inside of this function the origin is the center of the sphere. So I'm not going to be able to see anything right now because I'm going to have to move that ring up a little bit. Again, if you want to move something, you have to remap the origin for that particular function over here. So I'm going to remap it over here, vec2. So for the X, for left to right, we're going to stick it exactly in the middle, but we're going to have to move it up a little bit. And let's move it up exactly by the radius. So like that. So from left to right is going to be 0, and up and down is going to be 0.15. Okay, and there's our little ring. And let's make it a little bit smaller. Yeah, something like that, I guess, could work. I think that's good enough. All right, now the next thing I'm going to do is I'm going to make some filament that goes from here to there and from here to there. And for that, I'm going to have to write a function because I don't have anything for that right now. And again, I'm going to do this quickly. I explained this in the same video as the torus video below, so go check that out. So the distance to a line segment, and that's going to take as an input the ray marching position, which is position P, and then that line segment has a start and an end, right? So I'm going to call it A and B, and that's it. And then inside of here, I'm going to make some vectors. I'm going to make the vector AP, which is the vector from A to P. So that is P minus A. And I'm going to go AB, which is B minus A. Okay, let me just get rid of some spaces here. And next I'm going to calculate a value t, which is a value that is going to be 0 when we are at one point, when we're at point A, and it's going to be 1 when we're at point B, and it's going to be anywhere in between 0 and 1 when we're in between there, and it's going to be smaller than 0 or larger than 1 if we're outside. So for that I'm going to say float t equals the dot product of AP and AB, and then we have to normalize that, so I have to divide that by AB and AB. And now I can calculate a 3D position that is the position on the line segment that is the closest to point P, and I'll call that point C, and that is you start at one of the ends and then you go in the AB direction T steps. Okay, so like that kind of makes sense, right? Because if T is 0, then you just end up with point A. If T is 1, then you end up with A plus B minus A, which is B. So, and then we just return the distance from point P to this point C, which is the length of P minus C. Or what you could also do is you can also type distance P comma C. You know, that's the same thing as what I just wrote there, but I like it better like this, and most people on ShaderToy do it like this. All right, so let's see if this works. So I'm going to go over here. I'm going to say float line equals SD line segment. And I'm going to throw in there my ray marching position, and then the first end of the line segment should be right in the middle over here, which is this basically, but in 3D. So I'm going to do vec3 0, 0.15, 0, and then the other point that the line is going to go to is somewhere on the bar over here. So for that I'm going to go vec3, and so from left to right I know where that is. Well, actually, so from left to right here, if this is left and that is right, from left to right it's at 0, right? It's at exactly the same position as the ball, so that's 0. From top to bottom, I guess it's at 1.4 minus the radius, so 1.25 maybe? Oh no, hang on, this is a different radius. Well, very close to 1.4. 1.4 minus this, I think. 1.36, let's just try that, 1.36. And then from side to side, it is wherever this bar is, right? And the bar is at P.Z, it's at 0.4, we pushed it out 0.4, like that. So this is at 0.4. And that should give me an infinitely thin line segment, so we have to give it some thickness as well, so I can subtract something from here. And now I can union that in, so I can say D and a line. And that gives me a whole bunch of errors because this obviously is in 3D, not in 2D. Okay, and now we have a line. It's not a line segment, it's a line, and that's because over here my t value should be clamped between 0 and 1. Okay, so I'm going to go clamp, and go from 0 to 1. Okay, and that does that. Okay, so obviously I screwed up at the height, so let's just do it by hand and figure out something here. 1.9. Okay, so it's not 0.9. It's probably 1. Let's just make it 1. Okay, so now it's there. All right, that filament is a little bit thick, so let's make it thinner. Just make that smaller there. And now we need a filament that goes to the other side as well. And again, I could copy this and union the other side, but similar to how I did it before, we could just take the absolute of it. And over here, because I'm not using this p-value anymore, this is the last thing I'm doing here. What I could do over here is I could just change this over here like this to get me the other side for free. How cool is that? I think that deserves a sip of tea. Oh. Okay, well, it's good that I made it full screen because now I can see that the filament doesn't go all the way to the top either. So I guess we're gonna fix that. Okay, so for that, I guess over here, right? So 0.01 perhaps. Let me see if that. Go away, full screen. Okay. Yeah, that works. All right, perfect. All right, now one more thing here is that when we want to animate this, I want to be able to, in order to animate this, like it needs to be swinging back and forth, right? I'm gonna rotate this. So if I rotate this around the z-axis, then I should be able to do that. So for that, I'm going to add over here an angle. So I'm going to go float A for angle. And then over here, let's rotate. So I have to rotate the x, y, right? So x is from left to right, y is from top to bottom. I rotate that like that. And then I rotate that by an angle A. And then down here, I'm going to have to add that angle. So let me say A, float A equals, I could do I time, and that would give me that. Okay, so that rotates. Obviously, that's not what we wanted. We wanted to rotate around the attachment point. And for that, what we have to do is we have to, because this just rotates something around the origin. And similar to how I said multiple times before, if you want it somewhere else, you have to remap the origin. So let me just stop this for a second and put this over here. So the origin would be over here. And so here that would be, the origin is at 0, right? From left to right is at 0. It's at the same left and right as the ball itself. But at the y is higher, right? And it's at, I suppose it's at this point. Yeah. Okay, so let me just copy that. And then here I could say p dot y minus equals that. Okay, so now I remapped the height over here to the origin. And when we're done with that, we have to undo that. So now I have to say plus equals 1.01. All right, and that makes it that now it rotates around that point. Okay. Yeah, so, and then obviously we don't want it to rotate all the way, so we could make it a sine so that it starts swinging back and forth. Okay. All right, so now let's start putting in a few more balls. So let me just stop this and set it to 0, because I'm going to go, okay, so this would be, I'm going to have to make a few balls. So I call this the distance to the first ball. And then I'm going to have 5 balls. I'm going to have 1 in the middle, 2 on the left, and 2 on the right. So 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. Okay. And then I'm going to call these, let me just put some commas. I'm going to call these B2, B3, B4, B5. All right. And then we have to put them obviously at different locations. Actually, no. Let me just go here and say float balls equals the union of all of those, right? So min B1, comma min B2, comma min B3, comma min B4, comma B5. Like that, I hope. I did that correct. Yes. All right, so this, you just have to write it like this because min only takes two arguments. So if you have more than 2 arguments, then you have to kind of recurse like this. All right, so now we have to move the other balls. So we have to move them in the x direction. And by how much do we have to move them? Well, we have to move them by twice the radius of this ball, right? And the radius of the ball is 0.15, so this would be 0.3. Okay, and this would be 0.6. And then this would be minus 0.3, and this would be minus 0.6. Okay, so now we have all of them in there. All right, so let's see what that looks like when it animates. Okay, so now that's obviously not what we want. We kind of want the middle ones to stay put, and then the outside ball hits it, and then the other balls move. And so for that, because this A goes +1 to -1, right? So it goes +1 to -1. And so what we want to do for the outside balls at least is to cancel half of that so that it goes, let's say, positive, and then when it gets to 0, it stays at 0. And so for that, I can just say, I'll give you the minimum of 0 and A, and that just makes it that if A is positive, then it's just going to return 0. And if A is negative, it's going to return the negative value. So that's going to cut off half of the animation. That's why it stops here, but it does move the other way. And similarly for the other one, for the other side, we can do the max of 0 and A. So that gives me that. All right, and then we obviously want the middle ones not to move that much. I mean, in a perfect Newton's cradle that is theoretical and doesn't actually exist, it would be like that, right? Where the other balls are perfectly still and the momentum is perfectly carried over to the ball on the other side. But in the real world, obviously, it isn't like that. So let's see if we can make something. So, well, that's obviously way too much. So let's multiply that by some smaller value. 0.05 times 0.05. Okay, so now we have like that it moves a little bit. But now I want the outside, the last one, well, the last one flies off, but the second to last one, I also want that one to jump a little bit. And so for that, I'm going to use these same values, because obviously this ball needs to jump to the right, but it shouldn't jump to the left the same way, right? So, so let me take this out here and let me call this A1. And then over here, I'm gonna add this over here. I'm gonna say A1 equals that. I'm going to say A5 equals the other side, right? A5. Okay, so that shouldn't change anything. Okay, that's the same. And now I want to add that A1 and A5 to these balls as well. So over here I can say plus A1 And over here, I can say A plus A5. And that gives me that. And I think that looks pretty neat. So let me just make this go a little bit faster, so it's a bit more realistic. All right, so that's that. So that's where I'm going to stop this time. Yeah, in the next video we'll go over how to set up a material system and how to put some cool materials on this that make those balls reflective, and so you can see one ball in the other ball, and it's going to look all juicy and sexy. So yeah, I hope you liked this. If you did, please like and subscribe and click the bell icon so you don't miss the next video. Also, if you make something cool, if you make any cool Newton's Cradle or fireworks or whatever else, I would love to see it, and maybe I will feature it in my next video. So if you want that, then please let me know, either on the comments here or on the Facebook group. That would be great. But anyways, I hope you liked it, and I'll see you next time.